in this video, you will learn about finding the nth term of geometric sequence. And here is the formula for the nth term of geometric sequence. So we have our a sub n be equal to a sub 1 times the r raised to n minus 1. Well, the value of the r is equal to a sub n all over a sub n minus 1, for which the value of r is not equal to 0. And let us start with this problem. So here we would like to find the sixth term of the geometric sequence with a first term of negative 5 and a common ratio of positive 4. So to start with our solution, let us write first all the important information given in the problem. So here we would like to find the sixth term of the geometric sequence, and we are given with the value of the first term, which is negative 5. And we are also given with the common ratio, which is positive 4. So here we only need to apply the substitution property, for which we have to substitute these given values to their respective variables in the formula. So here we would like to solve for the a sub 6, so your a sub n should now be a sub 6. While for the value of the a sub 1, we have the negative 5, and for the value of the r, we have a positive 4. Since we have changed the n with a 6, so this n also changes to 6. And to simplify this resulting equation, we have to manipulate first this exponential expression, for which the exponent gives us 6 minus 1. Easily we will have an answer of 5. And now to simplify this exponential expression of 4 raised to 5, you have learned already in the grade 9 that this exponential expression could be expressed as 4 times 4 times 4 times 4 and times another 4, for which the base is the repeating numbers being used in the multiplication process, and the exponent tells us how many of this base should be used in the multiplication process. And now, to evaluate this exponential expression, we may multiply these numbers by pairs, like 4 times 4 gives us 16, and we may multiply this pair of numbers, which gives us 16 as well. And we are left with another 4. So here, I would like to multiply this pair of number first, and that would give us a 64. And now, we can multiply this 16 with a 64, and this gives us 1024. But we still have to multiply 1024 with negative 5. So let us use a scratch word for this. So anyway, we can easily do this like this. So since we are multiplying a negative value to a positive value, then that would give us negative 5,120. And now, let me check by having a scratch mark here. Okay, so we got the correct answer of negative 5,020. And that would be our sixth term of the geometric sequence. So in this video, you will learn about the geometric means. And let us start with the definition of geometric means. The geometric means are the terms between any two non-consecutive terms in a geometric sequence. And to further understand the idea relative to the definition of the geometric means, then let us have these examples. So here we would like to identify the geometric means between the indicated terms in the sequence. And here is our first question. What are the geometric means between the negative 6 and the negative 96 in the sequence? So here, we would like to locate the negative 6 and the negative 96 first in the sequence, and we have those terms here and the other one here. Now, you may notice that there are three terms found between those two non-consecutive terms, and they are the geometric means, which happens to be the 12, negative 24, and positive 48. Now, for number 2, our question is, what are the geometric means between 15 and 405 in this sequence? So here we would like to locate first the positive 15 right here, while the other given number is 405 right here. And you will notice that there are actually two terms found between those two, and they are the geometric means. Now, let us proceed with some basic problems involving the geometric means. And for our first problem, find the four geometric means between positive 2 and 486. To illustrate the idea of such problem, then, let us write the first number given, which happens to be 2. And since we would like to find four geometric means, then we would like to insert four blank spaces first before writing the other given, which happens to be 486. And now you will notice that we have a total of 1, 2, 3, 4, 5, and 6 terms. We may have an assumption that the first given number 2 is the first term in the sequence, while the sixth term in the sequence is the other given, 486. So at this point, you have learned in our previous lesson about the application of the nth term of geometric sequence, which has the formula of a sub n is equal to a sub 1 times r raised to n minus 1. So if we would like to run a data sufficiency test first before assuming that we could make use of such formula, then we may have our a sub 6 be the a sub n right here. So that means we will have a certain value that replaces the a sub n in this formula. And since we are given with the information about the first term or the a sub 1, then there will be a certain value that replaces this in our formula. So since we have made an assumption that our a sub 6 is the a sub n, then obviously this n right here also changes to 6. So now, you will notice that the resulting equation now only contains one unknown value, which happens to be the common ratio r. So this suggests that we could also make use of this formula for us to find the common ratio in the problem. And now, since we would like to have the a sub n be a sub 6, which has the value of 486, and our first term has the given value of 2, so we merely have to substitute such value, and our r is unknown for the meantime, and since we have our n is 6, so this n also changes to 6. And we have obtained such equation after applying the substitution property. And now let us manipulate and simplify this resulting equation for our answer. So having this exponent first, we have 6 minus 1, which happens to be equal to 5. So here we would like to isolate the r. So that means we should eliminate this numerical coefficient first by applying the division property of equality. So it only tells us to divide both sides of the equal sign by a certain number. So let's say to eradicate the 2, here we should divide this side of the equal sign by 2. And the division property tells us to do the same thing on the other side of the equal sign. Doing so, we have this be equal to 1, and we are only left with r raised to 5, while this one gives us 243. Now, let us try to answer this equation this way. So there is another way to come up with an answer here, but I would like to have my answer or my solution this way. So here I would like to write an equivalent exponential expression with 243 that uses 5 as an exponent. So meaning we are only looking for a certain base for which when raised to such exponent of 5 gives us the value of 243. So if you are already familiar with such exponential expression, then this would be very easy. But if you are not familiar yet, then you may apply the prime factorization or continuous division. Starting with 243, this number actually is divisible by 3. So let us start dividing 243 by 3. So here, it gives us 81. And now, let us do the same thing for 81. Dividing this by 3 gives us 27. By another 3, it gives us 9. And finally, by another 3, it gives us the quotient of 3. Now, you will notice that we have obtained same prime factors of 3. So, counting for the number of these same prime factors, we have 1, 2, 3, 4, and 5. So, that means 243 could also be written as an exponential expression of 3 raised to 5. So that simply means that the number that we are looking for here is the 3. And since we have obtained such expression both on the left and the right hand side of the equal sign to have such exponent of 5, then we can now simply concentrate on the common ratio which has the value of 3. So meaning we could try to disregard this first and just look at the number in our base. And that would be the value of your common ratio. Now, we use this common ratio for us to find the next successive terms after the first term too. And that is by multiplying the 3 with the preceding number. Doing so, if we multiply the 2 with 3, so it gives us the next number 6. And multiplying this again with 3, it gives us the next number 18. So we merely have to repeat this process. And now the geometric means are 6, 18, 54, and 162. In this video, you will learn about the geometric series. And let us start with the definition of a geometric series. A geometric series is the sum of the first n terms of a geometric sequence. The sum of the first n terms is denoted by S sub n. And now for our formula, we have S sub n is equal to A sub 1 times the quantity of 1 minus r raised to n closed quantity all over 1 minus r, where the value of r is equal to a sub n all over a sub n minus 1. You also have to remember the definition of geometric sequence, for which the common ratio is a non-zero real number. And let us proceed with a problem. So here we need to find the sum of the first 6 terms of the sequence. And the sequence has the first few terms of negative 2, positive 4, negative 8, and positive 16. So first, we would like to write all the important information that we can gather out of this problem. Starting with our first term of negative 2. And here, if you look at the formula, another information that is important is the common ratio. And here we have a certain formula for us to get the value of the common ratio, which is equal to a sub n all over a sub n minus 1. So it only means that if we, for example, assume that the a sub n is a sub 2, then your n changes to 2. So this would also be a sub 2. And this subscript will be reduced by 1, therefore The commonly used formula to find the common ratio is a sub 2 divided by a sub 1. Doing so, we have our second term, which is equal to 4, substituting such value. And for our first term, we have a negative 2. So replacing a sub 1 with a negative 2 gives us 4 divided by negative 2, which has a value of negative 2. So in this problem, our common ratio is negative 2. And now, let us substitute these values to their respective variables in our formula. Since we would like to find the sum of the first 6 terms of this geometric sequence, then we would like to write s sub 6. And for the first term, we have the value of negative 2. So writing negative 2 for the a sub 1. And here we have our common ratio with a value of negative 2. So you have to be careful writing your common ratio here, since the actual value of the common ratio is negative 2 and there is a minus sign in the formula. Please see to it that you will be writing the negative 2 inside the parentheses like this. And since we would like to find the sum of the first 6 terms, so your n changes to 6. And here our common ratio will be that same number, negative 2. And let us try to simplify this resulting equation. So starting here, of course, so our negative 2 is being raised with a positive 6. And that actually gives us a positive 64. Here we have 1 minus negative 2, which is 1 plus 2. That actually gives us a total of 3. And this actually gives us negative 63. So we may apply the cancellation method because we can easily divide the negative 63 by 3. Doing so, we have a value of negative 21. And negative 21 times negative 2 gives us positive 42. So the sum of the first 6 terms is positive 42. In this video, you will learn about the infinite geometric series. And before we start with the infinite geometric series, let us talk about the infinite geometric sequence first. So an infinite geometric sequence is actually a geometric sequence, so you are already familiar with these terms that actually presents a geometric sequence. Since that the sequence actually has an ellipsis here, this suggests that the geometric sequence actually goes on forever. Now, let us proceed with the infinite geometric series. So you know that a series actually pertains to the sum of the terms of a certain sequence, for which here we would like to have the sum of the infinite terms in an infinite geometric sequence. And just to give you an idea, let us have this example. So here are the first few terms of a geometric sequence, but here we would like to find the sum of all the terms. But there are infinitely many terms in this infinite geometric sequence. And here is the formula for the infinite geometric series, which happens to be S. And we have here the symbol for the infinite. So we are trying to get the sum of all the infinite terms in an infinite geometric sequence, which happens to be equal to a sub 1 all over 1 minus r, where we have the value of the common ratio be greater than negative 1 but less than positive 1. Or we may also say that the absolute value of the r is less than 1. You have also learned that in the definition of the common ratio, it is actually a non-zero real number. So here in our first problem, we would like to find the sum of all the terms in the given infinite geometric sequence. Now, there are only two quantities that we would like to know based on our formula, and those are the a sub 1 and the common ratio. So once we take a look at those information in our problem, we have our a sub 1 b equal to -2, while the common ratio b equal to the second term divided by the first term, which happens to be 4 divided by -2, which actually gives us -2. Before we actually start with the substitution process, let us try to make an inspection first with regards to this value of the common ratio, which happens to be equal to -2. So the condition for us to apply such formula for the sum of the infinite terms in a geometric sequence is that the absolute value of r should be less than 1. So here, if we take a look at this value of the common ratio, which happens to be a -2, so the absolute value of this -2 is actually a +2, for which it actually gives us a false statement, because +2 is not less than 1. It is actually greater than 1. Okay? So it is actually a false statement. So that means we will not apply such formula for us to find this sum of all the terms in this given infinite geometric sequence. So anyway, this formula is only applicable for such condition about the value of r. Anyway, just to give you an additional information, this formula is only applicable to convergent series. And now, this formula is not applicable for this divergent series. Let us have the next. Here we would like to find the sum of all the terms in the given infinite geometric sequence, and here is our sequence. You might have noticed that the absolute values of the terms in this geometric sequence are actually decreasing. And let us check what happens with regards to the value of the common ratio. And let us have the common ratio. So having the second term of 32 divided by the first term of 64. So here we have our common ratio b equal to 1/2. And now, let us have the absolute value of 1/2. So the absolute value of 1/2 is 1/2, which is actually less than 1. So it gives us a true statement. So since we have satisfied this given condition for the common ratio, then we can apply such formula for the sum of the infinite terms of infinite geometric sequence. And now, having the first term of +64 and our calculated value for the common ratio is 1/2. Let us substitute this information, the respective variables in the formula. So we have our a sub 1 be equal to 64, and we have our common ratio be equal to 1/2. So now let us start with the denominator. So here, 1 minus 1/2 is 1/2, and applying our knowledge on dividing this kind of numbers, then we must first write the numerator as it is, and we multiply the reciprocal of the denominator. So meaning we are just interchanging the position of the numerator and denominator. So here we have 1/2, and we will be writing this as 2/1, or simply 2. And multiplying 64 with 2 gives us 128. So that means that the sum of the infinite terms of this infinite geometric sequence is 128.